week 13. Hard to believe the semester is beginning to come to a close. As always, I need to remind you that this is recorded and live streamed. Today, I wanted to give people an opportunity to do a little bit of an update on where they were with their projects. I had asked people to try to dry run uploading their code to NanoHub and seeing if it runs, because I think it's pretty important. Even if what you have is very rough, it's pretty important that you go through the process that Giuliano showed to you to make sure that there aren't any deal breakers in terms of problems. Because one of the issues we face with NanoHub is that they can't, if they will fix problems, but they don't do it fast. And so if there's going to be a pull request for a problem solution, we need to get that in the next week or so if it's going to be done in time for the end of the semester. And so it's really critical that everybody try out the process of doing an upload, making sure that something runs there, creating a splash page. I'm not saying you have to publish it. In fact, I would say don't publish it because you don't want to lock that down. But do make sure. I'd like everybody to show where they are with things today. Again, what I'm asking for is not a long presentation, but I would like to see where people are so that if there are issues, we can address them. And then I want to come back to the feed-forward networks. At the end of class last time, we were talking about combining signals. We rushed through that a little bit. I'd like to come back to that and work on that a little bit more. And then after that, finally do the feed-forward network that we keep talking about, never quite get to. And at the end of the class, I hope, if we have time, to show you how to switch over to doing stochastic simulations, which only changes one line of code. And then begin to think about the difference between stochastic and deterministic simulations. So maybe I should let's start out with doing project updates. And we'll just maybe go just around the Zoom and see what people have. Show us quickly. Really, when I said no more than 5 minutes, I really meant it. I mean, I just want to make sure that everybody is making progress. I've met with a lot of groups individually, but I would like everybody to tell me where things are. And you take advantage of the class for expertise, your resources for each other. And so there's a lot of experience in the room. I encourage people to take advantage of that. So I guess we'll just start at the top left. Joel, what's up?
I can show, just give me a second. I was not in the page, but yeah, the project that I was working on was the analysis of Komarova's model. Let me just find it here. Give me a second. Not ready to be the first one.
We can come back to you. It's okay.
Okay. Yeah, if we can, because I have to grab it from somewhere.
Eden, do you want to go next then?
Yeah, sure. Okay, so let me just check. I think I'm just going to share my desktop. Okay. So Connor and I have gotten our app put together on NanoHub. We haven't published anything yet, but we've got the splash page working and everything along those lines. I think it's incredibly minimal right now. I think it's 3 sentences, but it's there and it exists. So that's all up and running. And in terms of the project itself, right now we've been testing everything in Tellurium basically, but like primarily writing it outside locally. So nothing that's written here has not been sort of checked that it's gonna work. And so what I have here is sort of our first lesson on applying dynamic systems theory to chemical systems. So, we're walking through, doing there's a lot of writing here, kind of walking through, what's an ODE, why does it apply? We've got some intuition checks along the way of interactive questions that they can answer. So it's not just a wall of text. And that's what these widgets are here. And then from there, we have some visualization. And right now, most of the dynamics in one dimension has been written out and described. And in terms of 2 dimensions, that writing still needs to be done, but we've also got, Connor, I don't know if you want to switch, because you can show the null lines, but
Yeah. Are you muted?
yeah.
Okay, cool. I didn't want to bombard everyone's ears. So this is pretty rough right now, but especially because my workflow is usually in Mathematica, but I've been working on kind of taking the plot that we did a few weeks ago in class and trying to show how you could do them with numerical approximations. So not for systems that you can't solve analytically. And so this is not polished. I need to change it to make it a function, but here I have a picture of phase space. I don't have the points labeled yet because I haven't written that code, but importantly, all that this function takes in is a tolerance factor for a cutoff point and the ODEs. And I solved it separately in Mathematica, and these are the null lines that you would get from this system. And as you can see here, I have it colored differently, so you can identify that there would be 3 fixed points in this 2D system. So the goal is to not just have the notebook be a general lesson on dynamical systems, but actually provide some code for numerical methods to generate the types of plots we've made analytically so far in this class. Yeah. Ends up that the resources for doing this kind of thing in Python are pretty slim. So it's been a lot of kind of hacking, looking at software that is designed to do this and kind of forcing some Python functions that weren't designed to do this type of thing to do this type of thing. So if you notice, there's a little bit of not jagged edges, but the lines aren't totally smooth in those null lines. And that might just be how it is for the way that I'm getting it, but they do approximate the null lines pretty closely.
Oh, sorry, didn't mean to interrupt.
I was just going to ask, is there a Python wrapper for XPP auth?
I genuinely don't know. I was also trying to only use things that would be, oh, we're both unmuted. I was also trying to only use things that I knew were in NanoHub. So I asked Juliana the other week about which libraries and packages were already available. So right now, what I just showed you is done entirely with matplotlib and NumPy. So there's minimal dependencies outside of the mainstream kind of Python packages that you'll find in most places.
There is
for XPPL. Okay. So that could be, maybe we should, would that be helpful for Nano? I didn't think to look for XPPL. I didn't see that though when I was scrolling through the available options.
I might look at it. We'd have to probably do a pull request to have them load the library. But it does do beautiful bifurcation finding and null line finding, at least in 2 dimensions. And so how you'd pass the model specification to it is something you'd have to think about. You might have to find an exporter. I don't know if there's an exporter or an importer for it. But it might be, what you're doing is fine, but it might be worth spending at least an hour looking at that to see if it may be more trouble than it's worth, but if it isn't,
no, that's good to know. I'll put that on my to-do list.
The other thing,
I just went, there does seem to be a Python library for it.
the other thing worth mentioning is Connor and I are sort of working on 2 apps side by side. The other one is sort of the chemical organization theory content we've talked about before. That one is, we're prioritizing the notebook we just showed. So that one is still in a place where we have about half of the principles I think we would need coded to release something confidently. That being said, that code is ready to go at this point. So that's going to be hopefully in the next week or so, we'll have the first one wrapped up, and then we'll be able to focus on debugging that one.
That's great. The one thing, since you brought it up, don't publish an incomplete notebook. Because one of the good things about NanoHub is also one of the bad things about NanoHub, which is when you publish something, it gets a DOI. And so you can't undo it. Once it's published, it's forever. So while you're working on it, work as much as you want and get it on NanoHub and make sure it works. But don't hit that publish button until you have something that you want people to see. Because once you put it up, getting rid of it is a pain. Because the whole point of it is to have a persistent identification so that the thing is there. But of course, persistence is a two-edged sword. But that's great. Okay, thank you. Let's go, Lindsay.
Yeah, sure.
I can
Yeah,
stream
Grant
it if
can
you want.
share. Yeah, go ahead. So ours is not there. That was a very interesting app and very polished looking presentation by Connor and Eden just now. We don't have any of the like text written out for the lessons or anything. And also it's not, the current version's not on NanoHub because, as I suspected, NanoHub does not support the version of 3D plotting that I was using to make the 3D plots interactive. That you could like twist with your mouse and stuff, which I still think is really important. I'm just gonna have to find another way to make it work. So what we're showing now is our like version that we've been working directly on.
So may I suggest that it's worth sending a pull request into NanoHub and ask them if they can make the library you need available.
Okay.
It can't do any harm. I mean, you may not hear back from them. The answer may be no, but asking them doesn't do any harm.
Okay, I may ask some questions later about how exactly to go about that. Oh, okay, or I could follow Pete's link. Okay, cool. So yeah, I haven't tried to do that, so this is the local version, as I've said. But we spent a little bit of time getting like user interface stuff up and running. And again, just to remind everybody what the context of the project is just that we are defining different sets of rules for an activity-dependent homeostatic plasticity mechanism and examining the way that those sets of rules affect the final solutions that come out of the system, where the system comes to rest. So if Grant wants to do some demonstrations.
So here in this collab notebook, we set up the widgets so that it's interactive. And we have these plots here. One's just a time series plot for all the parameters of interest. And then the other is a 3D plot of all the different ion channel concentrations. And the user of the notebook can go ahead and click on some presets here for all of the different parameter sets that were used in the paper that we're working off of. And they can also use custom values for all these time constants here. And they can see that, and it only does one run of the simulation so that it's fast and the user can go ahead and mess with it how they want without having to wait a long time. And then further on down, we set up this widget so that the user can run a full simulation with whatever parameters that they want. And so you can also have the papers parameters if you want to also see them alongside your own custom ones. And before I do that, I'm going to scroll down because it does change if you change it. And so this is the 3D plotting tool that we want to use, but doesn't seem to quite work with NanoHub just yet. And so it does allow, you know, the user to actually see all of the different sets of points here, where the orange is the starting cluster. And from here, you can do things like change the variance and starting position of your initial points, as well as change the parameter values. And all you have to do is set it up however you want it, and then click the simulate button. And that could take a few minutes, depending on how many points you do. And then after that, you can come down here and click plot, and that will plot out whatever the user wants to see. So that much did it.
Okay, great. I hope you can get the plotting routines up on NanoHub. It's a pain that they don't have it. And so I would definitely create a ticket as soon as possible, so you know one way or the other.
And so
Yeah. I will look at it.
And this is just a fixed plot of the paper's parameter values. And then down here, we have some correlation analysis if Lindsay wants to talk some about that.
I mean, I think we're out of time. Just suffice it to say that we have capabilities of calculating all these correlations. I just have to figure out how to present it to make it most interesting.
Okay, great. Again, the purpose today isn't to do an elaborate walkthrough. It's just to check in to make sure that everybody, if people are stuck, and so that everybody sees where everyone is, so that everyone in the class can help sort of synchronize with each other. Thank you very much. That's great. So Joel, are you ready next? Let's go for you next.
Yes, give me, okay, screen share. There we go. Okay, so I also didn't put anything on NanoHub yet. So everything is here on this collab. I was working with Sean, and we basically made everything very well divided in classes, so it's available in other places. And we were trying to establish a bifurcation function that could find divergence without having to look into the plots, because that would speed up things. So that was the last thing we did, and there is one. It's roughly working. But anyway, all of the information that is found here is actually better organized on this milestone report, where I put the type of the model according to Komarova's, the antimony same model but written in antimony language, a analysis here of the vector, the vector field of those informations, and a bifurcation analysis that's for every single one. Of course, this is done in one parameter. We were thinking on doing multiple parameters before we are ready to present this. The idea was having the user to change or to inflict a wound here and see this system recover or not, depending on how deep the wound is or how much damage is done in specific types of cells. But anyway, everything is half organized, I would say, but that's basically it, what we have to present.
Yeah, again, for the phase plane analysis and the bifurcations, you might talk to Connor and Eden, and if they do figure out a way to get XPP aught working on NanoHub,
Mhm.
It does a nice job doing those things. I mean, you've got one that works already, so you may not need it, but you might want to spend just an hour looking at that and seeing whether it provides functionality that would be helpful.
Right. Yeah. I'll plan to meet with Connor,
Great.
Eden, and
Okay.
If we're sticking with Komarova, I could probably go next.
That would work.
That's easy.
mean,
Also,
you
what's
may-
really interesting too about the bifurcations is what I noticed with when you go from the 2-stage system to the 3-stage system, all of a sudden, so the 2-stage system has, I mean, they have some bifurcations in negative population space but only like very simple ones in positive space. But once you hop over to the 3-stage system, all of a sudden you just get this explosion in complexity, and you get a bunch of codimension 2 or 3 bifurcations, which is so they're really hard to like kind of pin down, at least for where I'm at. But yeah, I haven't really found any codimension 1 bifurcations, at least in the 3, but that was only in 2 circuits of Komarova. It was the biologically accurate ones, the number 1 and number 2 out of the 3 stage circuits. But yeah, super interesting stuff. Love to talk more about that. But here I can share. So let's see. Just gotta allow, sorry, new laptop, and I've gotta allow Zoom to share my screen. All right, so we did get our project onto NanoHub, but I'm actually going to switch in a second to show you my other one because I kind of changed a little bit of the layout here, but same thing. So what we're doing is really getting a kind of nuanced understanding of the 2-stage circuits, just because, and the way that control is implemented, because we are noticing throughout the literature is that there was a couple of different options. So the main options, a couple of these are just playing around, but the main options were the ones that we saw in the Komarova papers. There's Arthur Lander has a bunch of really interesting work in the olfactory epithelium. So we were trying out his control functions, and then we also try out a Hill function, which I think I have them written out in LaTeX later on here. Yeah. So we have excitation and inhibition. Here's the Komarova versions. Then we get the Arthur Lander versions, and then we get the kind of generalized Hill form ones. But so actually what's interesting too is when I was doing this, I was sitting with Connor the other day, and I was sobbing because I couldn't get my this to work, the interacting thing, because something about the way I was doing the model, the parameters weren't going right. So I need to do that. That's probably the one thing I'm hung up on. But the rest of it is, most of our dynamical systems analysis is in Mathematica. So it's right now, it's similar to what Joel was just talking about. It's going to be the that fun problem of trying to get the stuff that we have done in Mathematica into Python. But at least just the way that I work is I just kind of toy around with it in Mathematica first, just so I can get that kind of intuition of what the system's doing. And then I'll worry about grinding out Python later. Our model looks very similar. So when we were first starting, Joel was showing us how he did his, which was super helpful, super amazing. Really helped us hit the ground running. Ours is a little bit different. I mean, the different variable names, but and parameter stuff, but at the end of the day, it's the same principle. But also too, I found some really interesting work. And I've been diving into it, like Axelrod, actually, the guy, the big game theory guy, has worked with Komarova, and he found 2 other circuits, I think one both in the 2-stage and in the 3-stage that are more biologically accurate that I didn't notice before. And so it's going to be fun to play around with using control, at least on the way that differentiated cells die. So that's what he also uses. So we'll probably be putting that in as well. But yeah, don't want to take up too much time, but that's kind of where we're at. We're again just got to put in the dynamical systems analysis for both of these phage things, and we also wanted to play around with perturbations because, like, I mean, these ones. So this model right here that you can see, this is a 3-stage. Here's the parameters, and I use Komarova type control for each one of them. But it's really pretty. I mean, the oscillations, of course, are super, super wonderful. And when you do perturb the system, so like, you know, like if you were to do I don't know if I want to do this live because stuff always messes up when you do it live. But if you were to do at time, you know, greater than 10 or whatever, you'd be able to see that they have these really wonderful oscillations.
Why not try
yeah,
it?
really cool.
Try it. If it fails, it fails. If it works, it works. We just won't debug it if it fails.
Or let's see, 200 or 300, let's say, or 500. Let's say 1. Oh, I gotta run the whole thing here, right? Let's see. I'm not used to doing it in the run all, right? There we go.
Yeah. What did it object to? Let's see.
Unexpected equal sign.
Oh, it's because why should that be? Okay, well, I guess I said if we can't.
That's fine. That's fine.
It's okay.
But
it's okay.
you can
Don't
believe
worry.
me. You can see these really cool oscillations. But yeah, in the full thing, we'll have it working. Eden's laughing. All right, that's our update.
Okay, great. Thank you, Peter.
Oh. I have my abstract put up, and here's the splash page. Then the model was, I'll scroll to the top. I have a bit of an introduction at the top. Then I have some plots here where it's just a very rough draft, so I'm going to delete a lot of these things. But the main simulation I have right now is one where you get to compare the effects of different radiation intensities on a senescing cell and what are the ROS concentrations. So the goal here is to have the user observe the point where there's a bifurcation. And if you don't get the answer, it'll tell you below, okay, you need exactly 9 grays of radiation. So after that, I have a lot of plots where each of these is a delay and the different amounts of radiation where I like push the system and see how much of a kick you need to get a different protein into the other steady state. So below that, I have a simulation that's regarding P38. You can see I have some text, but it's very rough right now. The goal here is P38 is going to be our inhibitor for ROS, and we want to see if it will indeed reduce the amount of ROS. So if you adjust what day P38 is added in, then it has a different effect on the system. Sometimes it will fix senescence, sometimes it won't, or prevent it, I should say. And the one on the right, meanwhile, is one where there's no inhibition. It's just kind of a control group. So I think that'll be helpful in seeing how things change. And beyond that, it's a lot of playing around. One thing I'm considering, though, is being able to use these clicker buttons to be able to cycle through some of the parameters. But that's all I have.
Well, that's great. People are digging into user interface a lot more this semester than they have in the past. I'm impressed. They're using buttons to just change the display, trying to do 3D graphics. So that's something that people are digging into, which I'm impressed by. Appreciate. The other thing that is bit new this semester, I think, is that people are actually doing code generation. Some people are actually generating antimony strings, and that's also something that historically people haven't done a lot of. So it's nice to see that going on. Again, for today, the goal was just a quick check-in. Thank you very much. So I guess Supriya and Danusha, where are things going for you?
Hi. We were able to push our initial code to the Nano Hub. It's still pending with the confirmation from the tool users. And apart from that, let me share my screen so that I can show you what we are doing. So yeah, we are waiting. So the tool is created, but we are waiting for the confirmation. Along with that, we just replicated our existing paper. One sec. So, is it the screen? Yeah. So we are replicating the paper which was shared earlier, and we were trying to get the values of EGFR and IGFR as of now. We need a lot of modifications in that, but still we are working on it. We'll add the decorators as well. That is in the pipeline. The next coming week, we'll be working on the decorators. So as of now, we have this much, this the analysis. So nothing much we've done till now. But yeah, everything was due by next week.
We are hoping to develop the program by the next submission. Like we are planning to get more clarity on the subject and then write more codes and implementations for that.
Is there anything you need specific help with at this point in terms of, I mean, I don't know what that plot is supposed to be doing. It looks like everything is going to zero, which may be fine. But at
Is
least,
it breaking for me or is it breaking for everyone?
but you are able to get things up to NanoHub and run them there. I mean, you could always, if you want to see whether your code could run on NanoHub, you could always upload it into Tellurium and run it in the NanoHub Tellurium. Even if you don't do a full upload. In other words, you could upload it by hand into launch NanoHub Tellurium, load your code in there and run it in there.
Yep.
And at least then you'll know if the libraries are there
Because
and if the GUIs are there.
Our initial code was running on local. We installed Tellurium and it was up and running in Tellurium in my local. But then we had to collaborate a few of the codes and we have to discuss. So we moved our code to GoLab.
Right, but you have to put it on NanoHub. So the goal here is to try. What I'm saying is that you don't have to do a GitHub repository and put it on NanoHub as an app to check if it will run on NanoHub.
Yep.
You can run the standard NanoHub Tellurium app, upload it as a file, and then run it that way. And that will at least check to see if the NanoHub libraries are compatible with what you're trying to do.
Okay, sure. We'll work on that. Thank you.
also, since you're waiting for NanoHub, would you mind showing that NanoHub page again, just so
Yeah,
that I
sure.
can be sure that there is nothing wrong on their end, since we are here. Okay, could you scroll down? So they are waiting for you. You need to hit the my code is committed, working and ready to be installed. Then they will actually get it on NanoHub.
Okay, so I need to click on.
Yes.
Right. The thing you don't want to do is the further steps in that workflow, which say it's my final code and I want to publish it.
Now they're gonna get it online, and you're gonna have an opportunity to actually test it as a proper tool, but it's not gonna be public until you tell NanoHub to make it so.
Did anybody else have problems with this step? 'Cause maybe we need to be clearer about this. Again, there's always this issue of making code publicly available is always a little bit more cumbersome than doing things locally. And that's why we're doing this here today, to make sure that nobody runs into problems in 2 weeks or 3 weeks when it has to be final. So. Okay, did I miss anybody? Or is that everybody? Okay, thank you for the updates. I appreciate people keeping them short. I'm glad that things are working for people more or less. I realize that trying to get everything done this early is not easy. And again, the goal is that when you're doing these publicly deployed software, you can't rush it. It's not something you could do in a day. And so the reason we're putting in these early deadlines is to make sure that people don't get stuck at the end of the semester trying to do things that just can't be done in a short amount of time. All right, so I'd like to come back to where we were last time. And I want to start out by thinking about sequential activators and inhibitors as Boolean operators. We did this. And at least when we talked about fixed points, it was sort of dull. A sequence of 2 controls always gave the same result as 1 control. 2 activators is the same as 1 activator. 2 inhibitors in a row is the same as 1 activator. Activator followed by inhibitor, inhibitor followed by activator is the same as an inhibitor. Not very exciting. And then we looked at the time it took for our single stage activator to reach a threshold. Because when you're going to string things in sequence, what matters is that when the thing in your input reaches the Hill function K, capital K in the denominator. And we were looking at how that time depends on various parameters in the system. And fundamentally, that time, if the K value is half or less of the maximum value, then the time depends essentially on the slope at 0. On the other hand, if you get close to having the maximum possible value of your circuit be the threshold, then it can take a long time. And of course, if your threshold is above the maximum value, you never reach it. And so you have these kinds of plots that we see here, where for most values here of P1, the time is relatively independent of P1. But if the input is too small, then it takes a very long time or forever. And then we looked at a series of operations. P1 activates P2, activates P3. And here we turned on P1 as a value of 1 at some early time. As soon as P1 goes up, it crosses the value of K1 for P2. And so then P2 starts to come up. When P2 crosses the value of K for P3, then P3 begins to come up. And so what you get is a delay in the activation of P3. And you could ask, how long is that delay? And in this case, it's the time it takes for P2 to get started, plus, in this case, log 2 over the rate constant for P3. Now, to build our network, we have to have two circuits come in and combine. And at the end of class last time, we were talking about that combination. And we mentioned that biologically, there are a lot of possibilities for this. There are a lot of different combinations that occur. And in real biological regulation, often there are many, many, many signals that combine to regulate gene expression. And those signals don't only act on the gene, you also have post-translational regulation of various kinds, which we're not going to talk about at the moment. But we thought about the two simplest cases, which is you have two input signals that you imagine acting on the expression of the gene. And the simplest things that you could imagine are that you need both of the signals to be turned on to have the gene active, or the gene turns on when either signal is. It's either an AND or an OR. Of course, you could have an inhibitor with an AND or an OR as well. If P2 is turned on, then the gene is off instead of the other way around. It doesn't really change the mathematics very much. But when we're going to use Hill functions, we have to think a little bit about what we want. For an AND, we want the output to be bigger than, we'll assume our K value is 1/2, our scale is 1/2, only if both of the inputs are bigger than 1/2. And if either input is 1, we want the output to be what you'd get if you only had one input instead of 2. If either input is 0, we want the output to be 0 no matter what. We did that together and it worked pretty well. For OR, things were a little bit more complicated. If either input was 0, we wanted the other output to be our Hill function. That winds up being a little bit more difficult to get to work. If either input is 1, we want the output to be 1 no matter what. It winds up that AND is fundamentally a multiplication operator as a logical statement. And so since our Hill functions are scaled between 0 and 1, multiplying two Hill functions together gives us something that's also between 0 and 1. And so multiplication works fine for an AND. There are other AND functions you could do, by the way, and again, Herbert's textbook talks about these. But the example he has here, here's your promoter site, and if A or B bind separately, it doesn't turn on the gene. You have to have A and B both bound to turn on the gene. And a Hill function like this, which is just the product of the concentrations of X1 and X2, works all right. And it has the desired property that if either X1 or X2 is 0, you get 0. If one of them is 1, you get the Hill function of the other. And if they're both turned on, the value is always between 0 and 1. For intermediate values, you max out somewhere in the middle. And so the bounds are preserved the way you'd like. And so we did that together. And now I'd like to come back to the one we were working on just at the end of the class, and maybe start out with a little bit of an exercise coming back, because I think we rushed that a little bit last week, which was how do we do an OR function? And again, the simplest thing that we could imagine would be just adding the two hill functions instead of multiplying them. And that in some ways behaves the way we want. On the other hand, if our value were given by the sum, our output is not going to be in the range 0 to 1, it's going to be in the range 0 to 2. And so that's wasn't in our product, in our project specification. We might accept it, but it's not what we said we wanted. And so then we have to think about it. On the other hand, if we divide by 2, then if we have either on its own, we don't recover our threshold. And so this one is a little bit more complicated. And there are many ways you could resolve this problem, but there are two which occur biologically. One is called competitive binding. And this is a very simple idea. You have one promoter site, and if molecule A binds to the promoter site, it turns the G dot. If molecule B binds to the promoter site, it turns the G dot. In which case, fundamentally, you have one hill function, which is whatever binding is, and the rate. And the concentration is effectively twice what it would be. But since the hill function is a function of the concentration, it's still between 0 and 1. Doubling the concentration just moves you to the left or the right. It doesn't change the output values. So that's competitive binding. A non-competitive binding, you have two binding sites, the way we did for AND. And then it behaves as if X1 and X2 are independent. So the first one is easier to think about. The second one takes a little bit more thought. So let's just come back and do this as a quick exercise. We did this exercise together, but I'd like people to try it again. We'll start out with the competitive binding case. Here, effectively, X1 and X2 are interchangeable. And so the amount of stuff that can bind is X1 plus X2. And we have a hill function of X1 plus X2. And so let's go back, and I'll ask you to write, you probably have it, you should have it from last week. Get your program that plots G of X1 comma X2 as a function of X1. And then scan different values of X2. So you do a little parameter scan where you overlay the plots. And just get that working, everybody. Here we're just plotting a function, which is X1 plus X2 over 0.5 to the n, X1 plus X2 to the n.
Oh, yeah, well, so yeah, in terms of each other, I guess.
And so you change the value of X1. And you could do that with something. You could say that X1 dot is equal to a constant, and then make it a time series. And then you could loop over X2 and overlay the plots. Does anybody have something that works, maybe as an example then, that you could show, somebody could show how they did it? I mean, this is the kind of thing that I'm looking for, and this code is available in the directory if you want it. Does somebody want to show what they have? Maybe again, this is too simple. People are trying to do something more elaborate than is needed. You don't need antimony at all to do this plot. You could do it perfectly well just in Python. Although having it in antimony is nice for other purposes. Giuliano, maybe I could ask you to pull up that old plot function, that plot hilda or. on telluriums while I'm working with people so that we could show them how the code looks. Or I can open it myself.
I've got a working version, I think. Which I can share.
Okay, great. Let's take a look. I was just going to cut and paste my version into the chat, but because of the character limit, I have to do it in 2 chunks. So that's why it was taking me a second.
So this is partially based off of one of the demos you had sent around, and it's adjacent to what we did last class too. But the equation is defined here. If you can see that highlight, I hope. And I'm mostly saying that I think this might be it because this plot looks like what you had on the slide. Because at first what I was getting is I was getting everything. I had a function that like sort of the y-axis, the y-intercept is what was changing, and everything was still meeting at 0.5 for a while. But I think it was because I had both s and s, or x1 and x2 going to the n, going to the exponent, and that was my problem for a while.
Right. Well, that's exactly the issue with the OR.
Yeah.
Which is, how do you do that combination? And so what you have here, it looks great. Let's look at it together and ask, does this do something? I mean, the first thing to say is that there are biological circuits that work this way. So this is a possible thing that does happen biologically. And so it's not a wrong solution, but you'll notice that let's look at the results together. And I put the code in the chat so everybody has it. So please grab that and have it to work with. What you'll notice here is that as a function of x1, the output is always between 0 and 1, which is what we want. And if x2 is 0, which is the blue line at the bottom, then x2, I mean, the value as a function of x1 is just the Hill function. It's just the sigmoid with the inflection point at 0.5. And if I make x2 bigger, then as x2 becomes bigger, my curve moves to the left. That is, the amount of x1 that I need to turn the circuit on goes down, because the turn on is the sum of x1 plus x2. So that means that if x2 were equal to 1, then x1 doesn't matter anymore. The circuit's always on. So this is a reasonably well-behaved outcome. And I'd like, and now what would be interesting in the next exercise, everybody should maybe grab this code, make sure it works for you. But let me take the screen share back for a sec, and then you could maybe do this. Why don't we'll have you do this in front of everybody, perhaps. Now let's assume that we have what's called non-competitive binding, which is my gene turns on if A binds, or if B binds, or if both bind. And the way to do that is the one that I think you said you did, which is that you have x1 exponentiated at x2 exponentiated, separately instead of as together. Now, you could imagine x1 to the n over 0.5 to the n plus x1 to the n plus x2 to the n over 0.5 to the n plus x2 to the n. Why don't we just try that? Why don't you screen share your code? And let's try looking at what happens when you do that. So let's do that together.
Okay.
So
I started to here to define a second
Right.
function,
okay, that would be fine.
but I have not finished it yet.
Okay, that's all right. That looks good. Yeah.
Yes, if I run that. This is what I was getting before. Yeah.
Yeah, that looks reasonable to me. It also goes between 0 and 1. It's also true that if x2 is 0, x1 gives you the sigmoid to begin with. It's also true that if x2 is 1, you always get 1. So all three of those things are satisfied, but the behavior is quite different. And so this was actually, this is the second exercise I wanted people to do. You've done it. The other one that you might try is the one that's in quote obvious, but it's less obvious, which is what if we simply added two hill functions together? So why don't you create a J3? And the rate could be the same, except now we're going to say the rate is VM times s to the n over 0.5 to the n plus s to the n. Quantity plus. So we add the two hill functions independently of each other. Does that clear? That would be the naive equivalent of multiplying them, right? We're going to add them as independent things. There we go.
And it's the same Vmax.
Yeah. We're plotting project. So now you'll notice it doesn't fulfill our design criteria, because if x2 is 1, our value goes between 1 and 2 rather than between 0 and 1. So that you get slightly different, you get something that doesn't make quite sense. So in this case, you do have to think a little bit more about how to combine them. And you've got three options here. That looks great. Okay. Did everybody get this running with the code that was shared or on your own? Does anybody need help with it?
I have a question. I don't
Sure.
understand why, if S is the thing that we're measuring, the thing that's getting turned on, then why is S also like one of the things that could competitively like bind to, I don't know. I guess I'm just confused.
Well, so here we're just looking at the rate of transfer. We're just writing a rate. We're not doing we're cheating a bit, because what we're displaying is J. In other words, I'm writing a rate law, which is at the rate at which S decays or something else. But in fact, what I care about is not what happens to S. What I care about is the rate. And so this is a not very elegant way. I could have done this in a variety of ways. I could have defined a function, which was the hill function. I could have forced S1 to scan by making S1 dot equal to 1 and running between times 0 and 1. That would scan the value of S1 between 0 and 1. I could have gone in Python and by hand incremented the value of S1. So I'm not really doing anything with ordinary differential equations at all. I'm just asking what the functional form of this, what the shape of this function is. And so I understand if it looks confusing to write it as a rate law when it's not a rate law, it's just a function. I could also have used my colon equal sign notation and said that G colon equals some function of X1 and X2. Or I could actually, we haven't talked about how to do function definitions in antimony, but I could do def function name parenthesis variable comma variable and return a value that way too. So there are a variety of ways of doing this. The way I have it here in our code is not particularly elegant, but I wrote it this way because I thought it would be the most familiar, given that we've been writing rate laws in the past. You'll notice what we're plotting though here is not S, we're plotting J, right? J of J3, so which is a function of S.
Okay, that probably was the main thing that I was missing.
Yeah. So the things we're plotting are not time dependent, but we're writing the thing as if it's time dependent. So it's not, you're right, it's not a very elegant way to do it, which is why I wanted people to try it on their own first before I gave you my code, because the code isn't great. Okay. Anybody else have a questions, comments about it? Now, of course, if we want to use those rate laws elsewhere, then we'll start writing rate equations. So that's why it's in that.
Professor Glazier, you're on mute.
I don't know how I got muted when I changed the screen share. Okay. So we noticed that they have these two rather different results. I put them side by side. In one case, the min and the max of our Hill function is the same, but the Hill function gets shifted to the left. In the other case, the maximum value of the Hill function stays the same, but the minimum value gets pushed up as I increase the other signal. The inflection point is, however, always at 1/2. And so these are two fundamentally different structures. And what I was going to ask you to do, and it's up to you, I'm happy that we could skip this little exercise if you want. It was more, and I was going to ask people maybe to break up into small groups to do it. So you could give me the feedback. Maybe it's not worth taking the time today, but it's something, so maybe not. Let's think about this. What I was going to ask you to do was, here we've done a parameter scan where we have X1 continuously changing and X2 is stepped. And this is really most informative if you do a little 3D plot where you have the value of G2 in the y-axis in the vertical direction, and then you have X1 and X2 horizontally. So you actually see the function in both directions. And so I was going to ask people to look up how to do in Matplotlib a 3D plot, and then generate the 3D plot for this. But I think for today, since we're already at 5:30, I don't want to not get through the feed forward network, and so I think I'm going to skip that exercise. But I'd encourage you. Several of you have shown 3D plots in your applications. but not everybody has done a 3D plot. And so this is a good place to try out looking up how to do 3D plots in a very simple context. And if you do a 3D plot of these two, what you'll see is that in the quadrant, x1 bigger than a half, x2 bigger than a half, both of these ORs are equal to 1. But the non-competitive OR, and in the quadrant, x1 is less than a half and x2 is less than a half. Both of them are 0. The difference is if x1 is less than a half and x2 is bigger than a half, then the behavior in those off-diagonal quadrants is different in the two cases. And so you'll see in a 3D that this corner and this corner are the same, but the intermediates have different shapes, and it's pretty dramatic when you go into 3D. And so if somebody wanted to try that out while I'm talking or offline and to send the code around, I think it's a nice example. One thing that we have to think about a little bit when we're going to combine these functions is we've always assumed here that x1 and x2 both go between 0 and 1, which meant that our k value was 1/2 for both. In a real biological system, the concentrations wouldn't always be scaled to 0 to 1. And so you might have to do that rescaling where to combine things, we have to take our whatever our concentrations are, here I've called them P1 and P2, and rescale them so that they're always scaled. To combine them, you have to rescale them by whatever their half maximal K is. Otherwise, one of them will dominate. If I don't do the scaling, I always have to map things back to that 0 to 1 range to be continuous. Again, if you think about digital logic, if some of your circuits operate between 0 and 5 volts and some operate between 0 and 12 volts, you can't connect them together. And so you just have to remember that you have to scale if things are not pre-scaled for you. And so, again, in general, if you divide through by that half maximal value, then everything can be combined in a consistent. So now let's actually talk about the thing that we've been alluding to for a long time, which is the temporal behavior of feed-forward networks. We know that for a network like C1, where we have P1 activate, P2 activate P3, P1 activate P3 directly, the steady state is going to be independent of the fact that we have two pathways, at least if as a function of P1. If P1 is low, P3 will be low. If P1 is high, P3 will be high. And so the equilibrium values of these are not so interesting for the what are called coherent networks. But the direct signal from P1 to P3 happens rapidly, whereas the signal via P2 is delayed. And so now the signal coming at P3 is going to have a fast component and a slow component. And of course, people who've done neuroscience are used to having things happening at multiple time scales at the same time in more complex situations than this one. But now we can think about circuits that turn on and off in particular ways because of this temporal combination. And in this case, we might imagine that the Ks are different. They may not be the same. Although to begin with, we could assume it's. So let's actually I'm looking at this because I thought I had gotten all the exercises renumbered for this week. And when I see this, I hope that I'm not lecturing out of the wrong slide deck. So let me double check something. It would be embarrassing if I had the wrong slide deck here. Yep. Okay, just my typo on the slide. So what I'd like people to do now is to write this network. And we're going to assume for the beginning that we have an AND interaction, because that's the easy one. And so that means that we're going to assume that the rate of change of P3 is the product of the signal coming in from P1 times the product coming in from P2. And so I would like people to write this circuit. You could write it as ODEs, which I don't prefer, or you could write it as reaction laws, which is fine, either way. And here are the parameter values I'd like people to use. And I'd like people to do the time dependence of P2 and P3. Start with P1 equal, you could do two things. The easiest thing to do is just to set P1 equal to some value between 0 and 1 times 0 and see what happens. It's a little prettier in terms of the plot if you start out with P1 equal to 0, 2, and then turn the value of P2 1 on with an event a little bit after the start of the simulation. So you see it go up like the step function that we did before. Okay, and so I'd like people to plot P2 and P3 versus time. If you use a step function on P1, then you'll have P1 as well as the variable. For this set of parameters, you'll notice here that the Hill exponent I'm using of 40 is not something that will ever be biologically meaningful. We're basically forcing a step function. We're making the thing Boolean. And we can play with that in a minute. And my question is, what is the time behavior of the circuit? Why do you think that is? Then you could try changing the rate. And the rate you would be changing is the rate here, which is the decay time of P2. And I want to see what's different when you change that. And then as a hint for the result, this is called a pulse generator. And I'd like you to tell me why. Okay, is that a clear assignment? Any questions about that?
I'm assuming P1 is constant, right? And do you want us to change that value over to, like, do an analysis over that one? No, right?
So to begin with, just start out with P1 equal to, so there are two things you could do. You choose. You could either start out with P1 equal to 0, and then at some short time, at time 2, have an event turn P1 to 1. Or you could simply start out with P1 equal to 1 from the beginning. Your plots will be prettier if you use the event. But it's not hugely different either.
All right, thank you.
And I guess Danusha and Supriya, since we haven't seen you do this yet, I'm going to ask you to show us the results for this. So please get those ready.
Okay.
And if people get ahead of the curve on this one, you could do what Joel was talking about, which is explore what happens when you change the rate constants, KD1, KD2, KD3. You could explore what happens when you change N. You could do a little scan where you change the value of P1 and see how this time probe behavior changes for different values of P1. But to begin with, assume P1 goes between 0 and 1. And it may be worth saying that this is biologically a pretty common motif. You see this relatively often in real control circuits. And by the way, there's a typo in this slide. Has anybody noticed it?
Is it in the Hill function? It's the lack of parentheses for, or no? I have it tiny on my screen.
I've written
Oh.
a feed-forward network, but what kind
Yeah.
of feed-forward network did I write?
So, okay, wait. All those are activators.
Mine isn't showing any kind of pulse behavior. It's just flat lines at 0 and 1.
Okay, why don't we screen share it and let's see what probably the thing to do is, why doesn't everybody take a screenshot of this slide so you have it as a reference? And then we can have, so you have that to reference, come back to. So I'll give you a second to do that. And then Lindsay, why don't we screen share and let's see if we can figure out what's going on, okay? Now we could share the code. If people get stuck, there is online code, feed forward incoherent pulse generator, available to try out. Everybody have the screenshot? Okay, so Lindsay, do you want to show us what you got?
Sure. And I grabbed the screenshot too, so that we can have both side by side.
Great.
Um,
People have had to watch me do split screen for a semester, so now we can watch everyone else do split screen for us.
it's not trivial. So yeah, I think this stuff was just this one was just copied from above. That's just an activation, which I think worked right before. And then of course, this is the new one, which I've gone over several times. And I don't see any typos, but there must be a typo somewhere.
So what I have something, there's one thing that I can see right away, which is, does anybody else see an issue that's the issue here? There could be an issue. One thing that you could do with this that could be helpful is to split the two circuits. So you could turn off, well, it's a little bit harder to do that with the way this is written. So, but there's something here that's going to cause a problem, which is your initial value of P2 is what?
1.
Right.
Oh, so it's
So-
already on.
So it's already on. In which
Okay.
case P1 isn't doing anything. So why don't we try there we go. So
And
this is looking a little bit more like it. So something is happening. P3 is okay.
It's maybe a little itty bitty pulse.
Yeah. So that looks better, perhaps. And then let's see about what else could be happening. K1, capital K1 is a half. Capital K2 is a half. They're all scaled to a half. That makes sense. And then KD3 is 0.2. And KD2 is 0.01. Why don't we try making, maybe KD3 is too big. Let's make KD3 smaller.
So like 0.05 or something.
Let's try that, see what happens.
Nope.
Does it make any difference? So what's happening here is that P2 is coming up rapidly. And it's turning off P3 quickly. So what I'd like to do somehow would be to turn off P2 and just have P1 act on P3 directly. Oh, I know why this is doing this. So this is an AND gate. So let's see what we could do that would maybe make this more interesting. Why don't we plot P2 by its, well, we see P2 by itself. And what's happening here is that for P3 to get turned on, we need P1 to be large and we need P3 to be small. So there's P2 by itself.
Oh, what else do you want me to plot?
Well, I'm trying to think about how to do this analysis. Let me look at my slide. Let's see how I did the analysis so that we can try. Let me see.
So should I stop? Should I stop sharing then?
No, hold on for a second. I just want to make sure I didn't make a mistake. It's certainly possible that I actually did something wrong in my analysis, because I know what my result was. On the other hand, I have that typo in the slide. So let me check to make sure that I didn't somehow actually do the analysis for a different network myself. So give me a second. Other people, are you getting the same thing or getting something different?
My code looks pretty much the exact same as Lindsay's does right now.
Okay, so let me look at mine and see if I made a mistake. See if I could find a mistake. So this is the code that I wrote. And I think it looks pretty much the same. Does somebody want to try that out and see what they get?
I can paste it in real fast.
For me, the code which is given in the drive, it's working fine. But when I'm writing it down on my own, it's giving a straight line.
Okay. Let's see whether we could figure out what's different about it. Yeah, that looks more like what I was expecting.
Yes. You have all of them starting off at 0. So maybe I try that with, oh, but you had the event structure for P1, that's why.
Right. I think it has to be something to do with the.
I think you made a constant. You make P1 constant with the $sign.
So if I just change mine to be like that. Oh,
Nope. Okay.
Well, you need to look at P3.
Yeah.
P2 is not. Okay, so P3 is not scaling right.
So why would, I don't think it being a $sign would make a difference, right? Because if it's not being, it's treating P1 as a parameter, and then the event is
Right.
just changing the value of the parameter.
Right, we're not taking anything out of P1. Right, it's a boundary species without the dollar sign.
It's
So it
true.
shouldn't be making a difference.
It's true.
Let's see what's different. Well, one thing that's different is in the one that we just ran, I had n equal to 4 instead of 40. So let's try making n bigger
On yours.
in mine. Let's see if. Yeah, that's what I was expecting. So let's see what's happening. What is different? K1 times D1, D2, P1 to the n over K1 to the n plus P1 to the n. That looks fine. The decay looks okay. And then we have the product of the two, K3, P3. All right, so let's compare that to what you have.
I copied what I had. Which I switched, I guess, the two terms. Maybe I could unswitch them.
No, that should, the order of the terms certainly shouldn't matter.
I know, but just for
Right,
seeing for comparison.
Oh, you have an extra K1 D1, but that's the, no, that's, okay, so that's, so you have, so I'm the one who doesn't have the extra K1 D1, is that right?
I mean, I guess at least according to the slide here.
So what, so I don't have that.
Yeah, right there.
So that's it, so that the other, so that this is another typo in my slide then. No, it's
And
that
you
K1
also have
D2.
K2 down there when I have K1 down here.
Right,
think.
although K1 and K2 are equal, so.
Yeah, that's true.
So that should give us, it's true that when you change things, that'll make a difference, but for the, it shouldn't change things now because we have K1 and K2 are both the 1/2. So I think the only thing that's different here is that in my version, I don't have that extra rate constant, K1, D1, D2. Which perhaps should be there. So let's try taking that out and seeing what it does. I think then they're identical. So in that case, the issue is the parameter values. Okay, so that looks all right. So the issue is the parameter value choice. So the one that I wrote wasn't quite the same. Is everybody able to get this to work for some version of the code? Because I'd like to come back and talk about the structure of the model, even if we've got it a little bit messed up. So one thing that we can do here is the time scale for P2 is controlled by K1, a little lowercase K1, which is 1 at the moment. Why don't we slow it down? Make that, instead of making it 1, make it 0.1. Okay. So now P3 stays on for a long time. And there's something funny here because this is set up so that, oh, I see how he did. Okay, so I'm sorry. Let's try changing KD2, which is actually the time code. Let's put KD1 back to what it was, which is 1. And now let's try changing KD2, which should change the rate. The way I scaled things is a little bit. So let's we had 0.01. If we make it 0.1, it'll be faster. You should see a short pulse. Yeah, boom. Okay, now make it slower. Yeah, there we go. And now make it smaller. Now make it 0.001. Now you're gonna have to change the time scale, stretch it out. So
Gotcha. Oh, man.
it's really slow. So maybe we made it too slow. Maybe make KD2 a little bit bigger.
Or,
Okay.
yeah. There we go.
So basically, the way this works is KD2 controls how long the thing stays turned on. And the other thing that we have to worry about then, KD3 will control the time scale for the turn on and turn off of P3. So let's try playing with KD3 a little bit. See what happens.
Okay, if it's bigger.
You can't really
doesn't-
see it very well.
yeah.
It changes what happens at time 0.
Oh, okay. Maybe if I go back to the previous version. Not quite there.
Yeah.
And then if I made it like smaller.
So you are seeing the 3 regimes that I was hoping you'd see, although we have to play around a little bit. So you're seeing 3 things, and this is the goal of this exercise. And I guess I need to go back and clean up the typos. We didn't catch. Giuliano and Hayden both looked at these slides, and we didn't catch. They caught a lot of typos, but they missed this one, unfortunately. And so I appreciate your patience as we get those typos fixed. But the key thing here, let's go back to the one we had with where it created the pulse. So we should probably.
I'm just gonna go to yours. Yeah.
That's good. Okay, fine. So we have this here. So here we have a pulse. And what we see is that P2 goes up continuously in time, but P3 goes up fast and then goes down again. Why is that? Because at short times, P3 is turned on by P1. But P2 takes time to turn on. As P2 goes up, P2 starts turning P3 off because we have an and-like behavior between our 2 circuits. And so what we get is that P1 turns on, P3 turns on, and then it turns off again. And the purpose of the homework problem would be to explore what controls how fast it turns on and how long it stays turned on for. And what we will see is the things that you actually saw, although we didn't talk about it much when we were playing. There are going to be some sets of parameters where P3 never turns on. Either the value of P1 never gets high enough, or P2 turns on so fast that P3 never has time to turn on. So if P2 turns on very quickly, then P3 never has a chance because P2 vetoes it. So the key question is P2 turned on faster or slower directly than P3 is? Does that make sense for people? Suppose that I didn't have P2 inhibits P3. I just have P1 turns on P3. That takes some amount of time. And so we could do that circuit. Let's see how we could do that one most easily. The easiest way to do that would be to force P2 to be 0. So if we do a $sign on P2 in that line at the bottom, I think that we'll see whether that works. I don't remember. It should work. Yeah, there we go. That forces P2 to 0. The circuits for P2 don't. So now we're seeing what P3 does by itself. That's P1 turns on P3, with nothing else. And you see in this case, it takes what, about 20 time unit, well, 10 time units to turn on. So now let's see what controls that time scale. And that time scale should be controlled by KD3. Let's take KD3 a little bit bigger and see if it's faster or slower. Is it faster? It's a little bit hard to see. Is it faster or slower, do you think?
Looks faster.
Faster. I think if we go the other way, it'll be clearer, make it slower.
Sorry to interrupt. It seems like in the J3 reaction, there should be K1 instead of K2 at the end. Is that right?
Let's see.
Yeah, that's what we were saying before, but they're equal. So it hasn't mattered
that
so
should be
far.
K1. Yes, absolutely. I mean, the code I provide is supposed to help, and I checked that it runs, but that doesn't mean it's right. So you're probably better at developing these things than I am by the time, at least with a group of you, you're probably better. Okay, so now we have P3. So now let's put P2, let's see if we can plot P2. P2 and P3 are going to be the same, right? Except that the values or the parameters are different. The functional form is the same. Right? They're both the same activator. Right? P1 activates P2, P1 activates P3, have the same structure. So the only thing that's going to differ is the rate KD2 and KD3. So if KD3 is big, then P3 is turned on directly quickly, and P2 is slow. So if KD2 is bigger than KD3, P2 will turn on faster than P3, and you'll never get anything. If KD2 is less than KD3, it will turn on slower, and then you should get a spike. So let's see if that works.
I was just trying to figure out how I could hold P2 constant for the purposes of P3 being good, but then also separately show P2.
Well, I guess what we could do,
I could make this like P naught or something like that.
well, I think the issue is P3, right? Because P3 is the one that has to have two values. P2 is, well, P2 was okay. You need two P3s.
Yeah, if I was just saying if I didn't want to rewrite the rate law, but I guess I could. So
You could call it something P3A if you wanted to. And then just take out the P2, the P2 component.
and remove this one.
You need the KD2, KD3.
Oh yeah. Yes.
There you go. And now you need to set P3A to 0 to start with.
And
now you
back
don't
P2.
need the dollar sign. Yeah. You don't need the dollar sign.
Okay.
That should be. Right, there you go.
I'll go
Right,
out a
so
little
it's-
further.
There you go. That's nice. P3A. Oh, J6 has it is missing an A in the rate.
Oh, yep.
There you go. So this is what's called a partial pulse. P2 and P3 turn on at the same rate. The direct ones turn on at the same rate. P2 starts fighting P3 for the AND on P3. You'd say P1 and P2 fight each other on P3. And that means that P3 starts turning on but never gets there. So now what we could do is we could slow down. Let's slow down P2. And we slow down P2 by making KD2 smaller. And what happened? Let's see, P3A. I wouldn't make it that much smaller. Maybe. Let's go back to where we were. Okay, let's go back to where we were. There we go. And let's just make it a factor of 2 small. Notice it goes up higher. And let's make it another factor of 2 smaller. Now we have to stretch it out a little bit. Our plot. There we go. So now we're getting something that looks like a pretty complete pulse. We'd still have to go a little bit further. Another factor of 2 maybe. And now you have the full pulse. So now let's put it back and do it the other way. Let's go back to where we started. And now let's make KD3 smaller. And now again, we're killing the pulse. Now let's make KD3 bigger. See what happens. So it's the relative values of KD2 and KD3 that matter. Make KD3 bigger again. Right? Make it even bigger. There you go. So if KD3 is much bigger than KD2, I get a pulse. If KD2 is much bigger than KD3, I get nothing at all. And if they're about equal, the pulse starts and never makes it all the way. Does that make sense to people? Now we could try some other things. What if there were an OR instead of an AND? What would happen? What if we had a different circuit? So this code now is the base code, this is good base code. So maybe I could ask you to put this code in the chat and everybody can launch it together.
So wait, was the follow-up question that you were asking when you said for the OR saying that if P1 or P2 can activate P3? Was that the?
Well, we have at the moment we have P1 and P2 activating P3. And so we could try P1 and P or P2 activating P3. Would be a different circuit. It's not going to behave the same way. Or we could change what the pattern of activators and inhibitors are. And let me just quickly, before we get too far into this, I want to I want to fix my code, my code in my slides, so I don't forget. Give me a second to do that. Because if I don't fix it now, I'll forget, and then what? But the slide will be wrong. But is it clear why this could be called a pulse generator now? So what's interesting here is that we're putting in a fixed value of P1. We're turning P1 on continuously. P3 comes up, either stays off, comes up a little bit and then goes off, or comes up, comes to maximal value, sits there for a while and then turns off. And the duration of the turn on and the turn off is defined by the KD2 and KD3. KD2 defines the bigger KD2 is, the faster it turns on. Sorry, the bigger KD3 is, the faster it turns on. The bigger KD2 is, the faster it turns off again. Does that make sense? So why doesn't everybody play with this a little bit and take a few minutes just to play with it and see what you get? See if it makes sense. So I have a set of slides that walk us through the whole analysis, but I'm going to just show the result. So the final result is that how big P3 gets, well, maybe let me walk you through it quickly. Okay, so what's happening here? We'll start with everything 0. And initially, we have 0 and 0 equals 0. So we get no P3. Now we make P1 1 at some time, early time. And one thing you could do is, instead of making P1 go to 1, you could make P1 go to a value that's intermediate. See what happens. And what happens is P1 goes to 1, P2 starts going up, and P3 starts going up. Why does P3 go up? P3 goes up because P2 is still small. So what do I see? Here, P3 starts coming up quickly. P2 comes up slowly. As I keep going, P3 comes up and it saturates. P2 is coming up, but it's still below the K that I need to turn off P3. At some point here, at this time, P2 reaches the value of K, 1/2. And so now it starts turning P3 off. And that little calculation we did last week of how long does it take to get to that K value tells us how long our pulse stays turned on. So that's how it works. And if we can analyze, if we want, how long it takes for each of these phases to occur. I'm not asking you to do that. So to get a pulse, P3 has to respond faster than P1. That is, KD3 has to be bigger than KD2. So here was the output that Lindsay showed us. Here was KD2 was 0.01, KD3 was 0.2. So KD3 is much bigger than KD1, and we get a full pulse. Here, KD2 is equal to KD3. The pulse begins to turn on and then dies. Here, KD2 is bigger than KD3, and we get a little glitch, but no pulse. So those are our possibilities. All right. So the next thing I'd like you to do, does everybody have that code and does it work for you? Before we go. All right. So the next thing I'd like people to do is make sure you get your pulse. And now instead of making P1 go from 0 to 1, make P1 go from 0 to 0.25, 0 to 0.5, and 0 to 0.75. And then the question is, what do you get? What happens to P3? Do you get a partial pulse, a saturated pulse, or no pulse? And does the duration, if you get a pulse, does the duration of the pulse change? So you run the same code, just change the event function to set P1, instead of setting it to 1, set it to 0 to 0.25. Set it to 0.5, set it to 0.75, only take you a minute. Key thing is to look at the results.
So am I getting any pulse? Okay. So when it is 0.25, I'm not getting any pulse. That's for P2.
So there's a glitch, a little glitch in Danusha's code. What is the glitch?
Looks like you're overriding the P1 value. So see where you say at the very bottom, at time greater than 10, P1 equals 1.
Mhm.
So this is actually more close to the plot for P1 equals 1. So you need to get rid of that if you're looking to hard set at 0.25 or make it become 0.25 there and make the initial condition 0.
Yeah, I wrote it here.
Okay, you could try running that. Let's see. Is that what other people get for 0.25?
Yeah, approximately.
That's sort of interesting. I'm not sure where that scalloping in P3 comes from. Supriya, do you want to show us your results for 0.25?
Yeah. So this is what I got for 0.25. So the P3, we do not have a pulse for P3. Right?
It's the same. I think
Okay,
it's the
so it's
same.
turned off. It's completely turned off. That's why it's
Yeah.
because
Mhm.
the Y scale is 0. Okay,
But when
great.
we are increasing to 0.5, we can see a little bit of pulse.
Great. So for that one, you might want to make the simulate a little bit longer. Make it maybe simulate to 500 instead of 300.
Mhm.
So you see better what's going on. There we go. So it's interesting here is, let's go to 1,000. Let's run it to 1,000. So what's happening here?
So till 200, we are seeing like there is an increase in pulse, and then with time it decreases as the value of P1 and P2 goes to a state steady state.
So what does P3 go to? The value of P3. What does P3 go to? This is actually an interesting result. So I think it's worth thinking about this one. Because this is a case I did not include in my initial result, in my initial list of possibilities. My initial list of possibilities was no pulse, a complete pulse, and a partial pulse. What's happening here? Does P3 turn on?
Yes.
Basically, it turns on. Depends, I guess, on what you mean by turn on, but it goes up and it saturates. But does it turn off? Doesn't turn off all the way.
No, it doesn't turn off, but it reduces its burst momentum.
Right. So this one is interesting because now we have something that turns on but doesn't turn off, which wasn't one of the cases we got originally. Okay. You want to try 0.75 since you've got it on the screen?
Yeah.
See what happens for 0.75. Great.
0.75 was zero.
So 0.75 and 1 look more or less the same. So 0.25, it never turns on. 0.75 to 1, it behaves like 1. 0.5 was interesting because it turns on but then doesn't turn off. So why don't we try exploring just a little bit around 0.5? Try 0.55. Maybe. See what happens. Okay, 0.55, we get a real pulse. So even just a little bit above 0.5, it gets the base pulse behavior. Why don't we try 0.45?
No pulse. So
No
5
pulse.
is the one where we start.
So 0.5 is special. It's a marginal case. So we probably couldn't do anything with that biologically because if you have to fine tune values very much, you don't get anything.
It's because if you do 0.5, it's equal to K1. If you change K1 to 0.53, for example, and do P1, 0.53, you have the same result.
Yeah. Great, thank you, Supriya. That was great. Appreciate that. Did anybody else have anything interesting they got out of that they wanted to show? Not at the moment. We could play with the parameters as well, and the Ks, the capital Ks, which are in this. Okay. So why don't we try something very simple? We've all got the code running. Let's switch the order of the inhibitor and the activator. So don't make the typo that I made. Remember that to make the inhibitor to the activator, you have P1 or P2 in the numerator to the end. The inhibitor, you have the capital K in the numerator to the end. So now flip the order. So P1 inhibits P2, P2 activates P3, and P1 activates P3. Can people try that and tell me what they get? Again, start with making P1 go between 0 and 1. So you only have to change 2 symbols in your simulation.
And so we're flipping P2 to activate P3 and P1 to inhibit P2.
Right.
That's right. So,
So J1 would change in the sense that we'd now have an inhibitor. So it'd be it would be K1 in the numerator of J1.
isn't
So
it
it
already
means
K1? Or do you mean,
So which one are you using? Because you're showing you're going to use the cell that's on the screen now.
yeah,
Okay, so the rate law for P2 is now that P2 is inhibited by P1. So you need to make, instead of having P1 in the numerator, you need K1 in the numerator. You have $P1 in the numerator now. You need to make that K1 in the numerator. And no $, because it's a parameter. Okay. And now in P3 rate law, where you have K2, that'll now be P2. All right. And then we need to change in E1 at the bottom of the event, it'll be P1 goes to 1, not 1.25. Okay, let's see what happens.
Don't you have to change on J5 too? P1 to K1?
Yeah, if you want to be consistent, if you want to see that one separately, yes. No $. Okay. Okay. And now P3A was just, let's see what happened. P3A was the output of what? P3A was,
P3A was just P1 activating P3 alone that we had
Right.
put in.
right, so P3 comes up initially because P0 is 0. And then it comes down when we turn on, I'm sorry, because P1 is 0. And it comes down again when P1 is turned on. And so here we should probably delay the time at which we turn on P1, make it turn on at 10 or 20. There. So now our default is that P3 is turned on. And now when we turn P1 on, it turns off P3. So this is not so exciting, actually. This is not a very exciting circuit from the point of view of this. Now, what we could do here is play with the timescales and see whether reversing the timescales here makes a difference. So this is one that we could play with. And I'm not going to spend a lot of time analyzing this one, but you get a different, the point is that you get a different result. What it could be used for is something that I don't have a good answer for at the moment. Let me come back to the results that I had. When I do it, I get something that looks like this. When I turn P1 on, P3 comes off immediately. Not very exciting. And you could ask the question, does that circuit ever occur? The answer is I don't know about that one. I don't know that I think that one occurs as often. Biologically. So the next thing that I wanted to do, and I do want to come to stochastic circuit before we run out of time, so I don't want to spend too much time on this, would be to have, here we turn P1 on and off abruptly. In fact, we turned one P1 on and left it on. One of the things that we could do would be turn P1 on and then turn it off again and see what happens. And so Well, we could do that with an event. Another way to do it would be to make P1 sinusoidally modulated. And so I'd like people, and I say break up into groups, but I don't think, and to explore different networks. Let's try doing it all together for one of them. Let's go back to our first network that P1 activating, P2 inhibiting, which was the C3 network that we were working on. Sorry, help. Where is it? P1 activating, P2 inhibiting. P1 activating, P2 inhibiting. There we go. It's this one, I1. It's the one we want. So we were looking. So let's go back to our I1 network. And now instead of having P1 0 and then switching up, make P1 a sinusoidally varying function of time. And now you'll have to make the simulation run a little bit longer. And now plot what happens to P3 as you change the period of it. And I'm not saying you should do that as a parameter sweep. Just try some different periods. You know that if you turn P1 on, P3 will come up, stay up, and then come down. So you'd expect if your frequency was fast compared to the time that takes, that you'd get one result. If your frequency was slow compared to that, you'd get a different result. Why don't you people try that? And remember, the syntax would be P1 colon equals here 0.5 plus 0.5 times sine of time, the reserved word, and then divided by some parameter, which is the period of oscillation. We haven't so far really talked, well, we did one example in the homework of an oscillatory circuit. And of course, biology is full of oscillatory circuits. The heart, the pulse in the heart, blood flow, cell cycle, circadian clocks, and so on. And quite often we want to respond in particular ways to those oscillatory behaviors. And so you can think of this very simple feed-forward network as a filter that acts on that circuit and behaves in a particular way. If the circuit takes, if our pulse generator takes a long time to turn on, then if our frequency of oscillation is fast, it'll never turn on, I think. You'll see. You'll tell me. If our pulse stays on for a long time, then maybe it averages and it doesn't care about the oscillations. So there are a lot of games you can play here. And let's see how it works. If anybody has something they'd like to show, let me know. Let us know, and let's look at it together. And here the parameter values I suggested are a little bit different. I would use the ones that we had before. I wouldn't use the ones that I have on the screen. I'd go back to the ones that we had that we had work a minute ago. I wouldn't rechange. So the workflow here would be go back to the one that generates the nice pulse, and then just change the one line instead of having an event on P1, say P1 colon equals 0.5 plus 0.5 times sine of time. And that period that you're dividing by will have to be fairly large because it has to be comparable or longer than the pulse duration. And let me know when somebody has something that works.
I think
Yeah.
mine's working.
Okay, let's take a look. That was pretty good.
So you wanted us to use the previous model, right?
Yeah, the original, the one with the one that we started with, not the one where I flipped the order.
Mm-hmm. So, I mean, I'm not sure what you would consider to be a fast oscillation or a low period, but when I do a low period, it seems that P3 is still activating.
Okay, that's interesting. And so you have, let's see, why don't we turn off why don't we not display P3A? Because that one's a little bit confusing
Yeah.
here. Let's just plot P3. And you need time too. Okay, so you'll have to, I think you'll have to have it quote time comma P2 comma P3 when you select your output. No, inside the square bracket. And you're missing a comma. There you go. Capital P2, capital P2.
Oh yeah.
Also need quotes around the P2 in between.
Oh, yes, sorry. There you go. So here you've got period being very fast, and P3 is basically tracking it, but it's staying pretty high. And now let's make the period longer. And here, see, P2 is still not stabilized, so you have to run it for a little bit longer. Yeah. There you go. So now you start out with long pulses, and now you're getting spikes.
Mm-hmm.
And now let's make the period even slower and see what happens. 20 would be fine. Okay.
It does seem like the activation time at its peak is getting lower and lower.
So again, here there are a lot of games you can play in terms of how that sinusoidal variation is turned into spikes. Right here you have continuous cycles. The amount of up and down is the same, but you're turning it into spikes. And of course, if you're used to things like neural networks, well, not neural networks, but neurons, where you get action potentials, you're used to continuous things getting turned into sharp spikes. So this is a very, very simple circuit, but in a neuron, you have something similar, which is your calcium and potassium channels are fighting each other. So you have a rapid turn on and then a turn off. And so you're seeing something a little bit like that here in a very simple way.
Mm-hmm.
Did anybody else get anything interesting from playing with this? There's a lot you can explore with it. So thank you, Grant. That was great. So I think I'll leave this exercise to the homework because we did that. And I'm sorry we didn't get a break today. But we seem to be people need to remind me about breaks. This is the second week when we missed one. So I'd like to now say, just in the homework, the idea was to try to explore some of these circuits. I certainly don't expect everybody to do all 8 circuits and every possible combination of turn on, turn off, pulse, and periodic oscillation. On the other hand, once you have one of these circuits written the way you have, switching between them is each time just changing a K in the numerator to a P or a P to a K in two places. So to run all of them doesn't take a lot of effort in terms of generating the code. It does take effort in terms of developing your understanding of how the different ones work. The other thing that we didn't play with a lot was how you change the Hill exponent. But we did see as the Hill exponent was small, we got smoother curves. As the Hill exponent got bigger, we got more step-like behaviors. Okay. So the last thing I want to do today, and we're not going to get very far, but I do want to introduce the idea and at least do one very quick exercise on it, is to deal with noise in biochemical networks. And there are a couple of different kinds of noise that occur in biological systems. When we're talking about chemical reactions or something like gene transcription, there's a fundamental stochasticity. If I have a chemical, each molecule of that chemical, if the molecule decays, it's like radioactive decay. That molecule sits there. There's some probability per unit of time of it decaying. It will decay at some time. And that decay time will be exponentially distributed. And that means that the time to decay, that the amount will decay exponentially in time. And the time to decay follows an exponential distribution. Each decay is independent. When we have two molecules react, we did that analysis a long time ago when we came up with the derivation of mass action. The two molecules that are going to react have to be close to each other. Now, exactly what close to each other means, and the fact that they probably have to have the right orientation as well as being close to each other, means that this is a complicated problem. But if the molecules are moving stochastically in space, they're Brownian walk, then even with a given density, there's some probability per unit time that the molecules either are or not within a given volume. And that's a random event. Now, when the reaction occurs, we no longer have the substrates of the reaction. And so then the reaction rate changes. And so all of the ODE work we've done has assumed that the concentrations of molecules are big enough that we can neglect the behavior of individual molecules, so we can treat a population average. Now, if we're talking about water or ATP, that's reasonable. There are plenty of them. But what about something like our gene? How many copies typically of a gene do we have in a cell? Somebody? Two. Often one of them is turned off, so it's one. So if you have one gene, which is your DNA, and you have one binding site for transcription factor, then that transcription factor is either bound or it isn't. It's a Boolean operator. And so the rate is determined, there is no rate. You either are bound or you're not bound. And the thing we're interpreting as a rate is the probability of that site being bound, of that gene being transcribed or not. When we look at transcription factors, those X1 and X2 that we were looking at, typically in a cell, we might have 5 or 10 of them. If we have 5 or 10 molecules distributed over a large volume of a cell, to treat that as a contiguous density is not really a very good idea. When we're talking about signaling molecules, we might be talking about 50 or 100 of them. And so again, whether we can treat that as continuous or not matters. If you're going to get infected with COVID or HIV, the difference between one replicating virus particle and 0 replicating virus particles is a big deal. If it's 0, you're not infected. To stay uninfected, it has to stay 0. Once you have 1, you're infected. The difference between 0 and 1 is big. That's a stochastic event. Those are all fundamental internal noise. Those are intrinsic to the system, the nature of chemical reaction. The other thing is external fluctuations. The temperature of the system changes. The light exposure changes. You shake the system. And so there are two fundamentally different kinds of noise in biochemical networks. The Gillespie algorithm, and we're not going to deal with the details of how the Gillespie algorithm works. It's definitely worth reading about. Basically, tries to deal with this by saying, I'm going to assume that there's some density of chemicals. Based on that density, I'm going to ask the question, do I, at any given instant, have two molecules in the same region at the same time by rolling the dice? And then if so, do they react or not, based on the reaction probability? Now, there are a whole variety of different ways of doing this. One of the problems with these stochastic algorithms is that they tend to get very slow when the number of molecules is high. Because in our world, we can scale everything. So far, we could scale everything by some typical concentration. In the world of probabilities, it matters whether we have actually 1 molecule or 10 molecules or 100 molecules. And so we can't rescale things when we go to the world of stochastic process. The other thing that happens is that Gillespie calculates when the reaction occurs. And that means that the time steps are not uniform. So when you run Gillespie in the normal default mode, if we don't usually look at the time column of our output, of our simulate output, but if we do, we'll see that there's a fixed time step. When we run Gillespie, we will see that the time intervals vary as well as the concentrations. And that's fine if we're plotting one thing, but if we want to overlay plots and do something like an H-stack, we have a problem because we don't necessarily run the simulation for the same amount of time twice, and the number of points we get are different, and the times at which we have points are different. And so there's some practical computational matters about how we deal with arrays where the x-axis for time has got different values. And one of the things that you can do, and you have to look this one up, I'm not going to show you how to do it, but it's in the manual. I don't usually say it's in the manual, but there are a few times when I've said that today, and this one is one, where you can tell it that it has to use a uniform step. And that's no longer a true Gillespie algorithm. It's a little bit different. And there actually is a beautiful textbook. I think I sent the ad for the QBio conference. There was a beautiful textbook that came out of one of the QBio conferences talking about all the different algorithms for doing stochastic chemical reactions. There are a lot of them. How do we make them fast? What do we do if we want real time steps? There are many, many issues. In particular, when you want to do large concentrations, these stochastic algorithms become impossibly slow, and the stochasticity no longer gets to be important. And so there's some interesting numerical mixed algorithms where when the concentration gets higher, you do more of it ODE-like. And when the concentration's low, you do it more stochastically. And you have to merge the two together. So there's some very interesting mathematics and computing about it. Okay. So Tellurium does allow us to use a Gillespie simulator rather than OD simulator. And again, in this case, the reaction rate is the probability per unit time that one molecular reaction occurs in the reference volume, whatever that means. And the syntax for this is model name, our usual, dot Gillespie instead of dot simulate, start time, comma, end time. And actually, I said I wasn't going to show you how to do the time step, but if you want to, you just say comma time step. Okay. One of the problems is that in this world, you're counting by molecules. And so if your concentrations are scaled to be less than 1, you have 0 molecules, so nothing happens. So your numerical values of your concentrations always have to be bigger than or equal to 1, or nothing will happen. And so what I'd like people to do in our last 10 minutes is write a very, very simple simulation. And again, you can neglect the model name, the comments, and everything else. And let's go back to our old friend. A, you don't even have to type the names of the reactions. Make it faster. A goes to B at a rate K1 times A. B goes to nothing at a rate K2 times B. Start with A equals 1,000, B equals 100. K1 is 0.3, K2 equals 0.1. Run this with simulate. Reset, run it with Gillespie, and plot. And tell me what happens. What's the tip? What do you get the same thing or not? Is that a clear assignment? I think it shouldn't take too long to write that. If you've got, everyone has Tellurium running. So, we're not going to get through all the exercises on this today. But I think it is important enough. I really wanted you to see this sooner rather than later. And the exercises that I was planning, which we're going to do, I guess, the week after Thanksgiving, if we have time, ask the question, as you increase the number of molecules, do you recover your original value? Does the stochastic simulation converge to the deterministic ODE simulation? The other one is, if you run lots of replicas of the stochastic simulation and try to average them, you recover the ODE simulation. And the answer for this very simple case is yes. But we will find that in more interesting cases, like some of the networks that we did in that problem where we looked at the different motifs, for some of those motifs, you get qualitatively different behaviors for the stochastic simulations and the ODEs, for the deterministic simulations. In particular, we did the toggle, and when we have a deterministic toggle, either A is big and B is small, or A is small and B is big. There's no alternative. Once you're in one state, you stay there unless you kick it. In the stochastic version of that simulation, you are spontaneously switching back and forth. You stay in one state for a while, then you flip to the other one, and then you flip back. And that's called chatter. And in particular, that means that the classic models of cell differentiation based on transcription factors cannot be how differentiation works. It can start differentiation, but it can't maintain it, because a latch cannot give you a stable, steady state. In dynamical systems, we tend to not. The whole point of dynamical systems, you don't have noise. When you start putting noise into dynamical systems, terrible things happen. And so for all the dynamical systems people in the room, this one is an interesting one to play with. For the people coming from neuroscience, of course, you're used to dealing with a contradiction, because in real neurons, everything is incredibly noisy. The spiking of action potentials is noisy. The intervals are noisy. The actual values are noisy. And so we tend to do these deterministic models of the amplitude of the spikes. And somehow we have things like echolocation by bats, where despite the uncertainty in spike timing and amplitude, the bat can have a temporal resolution of microseconds between its ears. Exactly how that works is pretty mysterious. So that's a harder set of problems than the one we're going to deal with today. But I just want to point out that the stochasticity is a very fundamental problem, and our mathematics are not really very good at it. Our ability to deal with stochastic differential equations is not great.
So are there, on the, note of it not being great, are there any like sources that would be good to poke at? Because just like in terms of this, right? Like to your point, for dynamical systems, I'm like, okay, I have these tools, I know how to go about it, starting with the time series and then going to these other things. Is there a place to look for anything even partially analogous for stochastic evolution of those time series, or is it really just back to like looking for patterns in the time series?
Well, it depends what the equations are. There are things like Langevin equation, which are, or stochastic differential equations, which have well-defined solutions. That's a little bit different from starting from a deterministic dynamical system and asking, when you add noise, what happens? And typically what happens is that as you add, for tiny amounts of noise, your fixed points fuzz out, your boundaries of your basins of attractions fuzz out, but things stay preserved up to a point, and then as you increase the noise, suddenly everything falls apart. But there are no guarantees of that. Depends a little bit on how close your fixed points are, what the order of, whether you're quadratic, cubic, and so things get pretty complicated pretty fast. And there is a lot of theory about random noise in different cases, but you don't have the beautiful bifurcation structures that you get in simple deterministic systems. Did anybody get a result for this that they want to show? We've got 4 minutes left. Somebody?
I've got, I think.
Okay, let's take a look.
Let's see. This is what I had.
Perfect. Great.
Yeah, and I can stretch it out more if people want to see where it put, but I think that's.
Yeah, that's fine. Let's try making A 100 and B 10.
Yeah.
So let's just before we change anything, let's just look at this.
Sure.
You'll notice that your stochastic line and your deterministic line are tracking each other pretty well.
Yeah.
Modulo a little bit of fluctuation. So what this is telling you is for 1,000 molecules, for this set of equations, assuming that it's deterministic is not a bad approximation. So this is telling us 1,000 is basically, but let's make it 10,000 and 1,000.
10,000 and 1,000. Okay.
Do that. They're not quite the same, but they're almost the same.
Yeah.
Given our ability to measure in biology, you wouldn't be able to tell these apart. Now let's go the other way. Let's make it 110. Well, would you say that this is an acceptable approximation or not? You want to vote on that?
Probably case dependent.
Well, how about 10 and 1?
Spot on.
Now, what's interesting is, if you could, can you run the Gillespie 10 times and then plot at the end so you can see the overlays, do the Gillespie multiple times.
Wait, so you want me to run this for a longer duration, or?
I'll just run it 10 independent times. So I want to see 10 different plots overlaid on.
Okay.
And you'll have to put the reset in. So that's the easiest way to do it.
Oh, you want the reset to be,
You need the reset or it won't work. You have to-
I mean, at that point, it's gonna reset though to blue and orange, right? I'll have to do them.
No, if the color cycle false, it'll be okay. Just reset. You need to do R dot reset all before you run it.
Oh, I understand. Sorry, I misunderstood. Okay,
So just
so
copy
then-
the 3 lines and paste them a few times.
yeah, okay. Oh, thank you. Okay,
Why don't you see if it works before you put paste
Fine.
it? There you go. Good.
yeah,
So this gives you a sense of how much variation you get between runs.
yeah, no, that's a lot.
With the answer being there's quite a bit. Now, since these are linear, you might expect that if I run it a lot of times and I average it, I get the same result as if I ran one with a lot of molecules. That may or may not actually be true in particular cases. And what kind of averaging I should use is also problematic. Is it a geometric average? Is it a normal arithmetic average? Should it be a median? There are a lot of possibilities. What do I do about time jitter? When Giuliano was working on infection, when you infect with a small number of particles, the time when the infection starts is highly variable, really highly variable. But if you average the value at a given time, it makes a total mess because what you have to do is you have to align the start times. If you don't align the start times and you average, you get garbage. And so you run into a lot of fundamental issues with how do you combine data sets when there's stochasticity. And even this very simple case will help you begin to understand that. So this is great. We're out of time for today, but I hope this gives you something to think about. I would like to spend the 2 topics I would like to still cover, modulo that we have to do presentations. I'd like to spend a little bit more time exploring stochasticity because there's a lot to do with it. And I would like to give at least one lecture on parameter fitting, which we haven't covered, and it's important. And I think we should have time to cover both of those things and have people do presentations before the end of the day. So are there any questions or comments then before we break for tonight? I realize next week is a holiday, which means everyone works. Maybe. I hope people are going off. That's a bit of a joke. I hope people are going to take at least some time off and get some rest. I hope you have some time to work and get some projects done. I know you have a lot of classes, and probably a lot of classes have projects. So this isn't the only thing you're doing. So any other comments or questions before we stop? Okay. Well, thank you, everybody. Have a good Thanksgiving. And I will see you in 2 weeks. I'm not going anywhere, so if people want to meet to talk about projects or other things between now and Thanksgiving, I'm available. And I want to appreciate everybody people were great about showing what they were doing. And again, there's no problem if you're stuck and you show your code and we work on it together to help get you through, that's fine. The point of this is always to learn. So thank you, good night, and I'll see you in 2 weeks.